Great, I can hear you. And so Laurentiu is from IPHT Saclay, and he'll tell us about stringy corrections from mixing color and kinematics. Laurentiu, please begin.
Hi, thanks, Lance. And I'd like to thank the organizers for inviting me to speak here. And I'll talk about some recent and some ongoing work with my collaborators, JJ, Zhangpeng, and our great PhD student, Suna, which is mostly about finding some new building blocks which help us express string amplitudes, low energy string amplitudes. So just on a short overview, first I'll just introduce the general amplitude bootstrap. Then I'll spend some time and discuss some IR and UV results and how you can fix CHY integrants from using UV considerations. And finally, I'll spend most of the time discussing these new ingredients where you mix color and kinematics in a new way. So the amplitude bootstrap. In short, the goal of the amplitude bootstrap is to find alternative but simpler definitions for amplitudes. And you might think, well, why do we need other definitions? We already have Lagrangians and Feynman diagrams. They just give us the answers. But of course, if you find that your answer is given by this, which is the 5-point glow and amplitude, you might hope that there could be better ways of computing these amplitudes. And so basically, there are two goals within this program. The first, which is more practical, I would say, is just answering the general question of how can you check expressions and know that they're fine. Say I give you this expression, how do you know it's correct, right? I mean, you could compute it all over again and check, but I mean, then you lost a lot of time. So we look for principles that fully constrain amplitudes. And in this case, it could be gauge invariance and unitarity, and you can check all of these things. And for this purpose, of course, it's very helpful to know what's the minimal amount of information you need. Right, and in this case, it turns out that just locality and gauge invariance is enough, which is very simple to check. But a deeper motivation for all this is to find some hidden structure. Right, so if you find, for example, that gauge invariance fully fixes an expression like this, you might be tempted to start looking for other variables which make gauge invariance manifest, but maybe you lose something else in the process. And of course, this is how you can get the Park-Taylor formula. See, in this expression, it's gauge invariance that's manifest, but you lose everything else. But of course, it's a much nicer expression, and I don't have to motivate further why we need expressions like this. Now, there's actually a lot you can do with this sort of bootstrap ideas. So here's a table with some of the recent results. These are all of the amplitudes you can get by using some of these principles. And what's nice about this table is that in none of these examples, you ever have to use unitarity, by which I mean factorization, since this is just tree level, I should say. So what this says is that, say, locality plus soft terms fully fixes Yang-Mills or everything that has an X over here. And these are the main principles you can use: gauge invariance, soft terms, or even some more general IR behavior, UV scaling, and color kinematics. And I'll discuss these three things. Now, one thing you immediately notice is how powerful soft terms and UV scaling is. Like almost every theory here is fixed by one of these or both, with some very strange exceptions, Bornefeld and DBI, but that's the way it is. And actually, it looks like it's a tie. It's 8 versus 8. So do we have a winner between these? And by the end of this talk, actually, yes, we'll have a definite winner between these. So the next part, I'll briefly discuss some results here and why these principles are so great. And then in the later part, I'll spend more time discussing in detail how you can build new color kinematic objects that are relevant for strings. So actually, probably the central concept here is that of soft terms. Most of these things can be proven, and if they can be proven, it's by using soft terms. So next I'll briefly discuss soft terms and why they become so important. And recently, of course, people have started wondering how we can use amplitudes and everything we've learned about amplitudes to learn more things about black hole scattering. But we can, of course, pose the question the other way around, and we should. So we can ask, what can black holes teach us about amplitudes? And a few years ago, it's been proposed that soft particles carry black hole information. And we can take this basic idea and turn it into an amplitudes question, which is how much amplitude information can soft particles carry? And the result is actually quite surprising. See, the naive answer is that the IR and the UV of an amplitude are disjoint. So if you take a soft limit where you send one momenta to 0, you get some formal Taylor expansion like this of an amplitude in the powers of Z. And you can sort of separate the first terms in the IR, which are the soft terms, and everything else you just put in the UV, which is soft term avoiding. And of course, you might say, well, okay, so these are completely different. The information here is totally disconnected from the information there. But it turns out that soft terms fully constrain almost all amplitudes. If an amplitude has a soft term, it's probably fully constrained by it. And it's a very simple way to see how that can happen. And this is the basic idea, is that the UV info of one particle is hidden in the IR of a different one. So take this simple example. This is some random term that can show up in the 4-point gluon amplitude. If you take P1 soft here, you find that this goes like order Z. So you might say, okay, this is in the UV. There's no soft term for it, so it's free to do whatever it wants. But of course, you can take P2 soft, and this one goes like 1 over Z, right? Because there's just a P2 downstairs. So actually, this term shows up in the soft term of particle 2. And what's really amazing is that any term you write down has this property that it shows up in at least one soft term, either leading or subleading. So this is basically conceptually why soft terms are enough to fully constrain amplitudes. And this is true for all amplitudes. Next are the UV constraints, which you might think will probably work in the same way. If some term shows up in the UV of a particle, but not another one, maybe a different particle has it, and so on. So all of these things are interrelated, but it's totally non-trivial how that can happen. Now, as for UV constraints, of course, the original motivation for these things was just to enable the BCFW recursion. So from a few years ago, we know that you need some scaling like this or better under some shift of, say, the momenta in the simplest case. And if you find that your amplitude has this scaling, then you can build it using a recursion. So that's great. But it turns out that the scaling alone is all you need. You don't need the recursion to build the amplitude. You don't need unitarity. You don't need to look at the residues. You don't need the seed amplitudes to build up high and higher. All you need is locality and just imposing the scaling. And this is enough for, again, most theories we know, Biajoint, Yang-Mills, Sigma model, Born-Infeld, and so on. And actually, this is surprising for some of these theories. You might say, well, it's not that weird, maybe for Yang-Mills, maybe it's just related to factorization or something. But if you look at Born-Infeld, Born-Infeld is not fixed by locality, unitarity, or gauge invariance all put together, because it has contact terms that are just gauge invariant. So none of these constraints can touch it. Of course, a few years ago, these people realized that you can do some chiral soft limits which do fix it. And now this is the opposite. You can do some UV shift and that fixes Born-Infeld. So again, it's quite strange that you have this UV versus IR both fix Born-Infeld. You might start thinking how maybe these things are related in some way. And of course, even more recently, people are looking at fixing GR integrands by using UV constraints. So that's great. It seems like it's a very universal feature of amplitudes. And in fact, again, almost any amplitudes you can think of, including higher derivative corrections coming from string theory or whatever, all of these will have some better than expected scaling. Now, in most cases, the scaling is not enough to fully fix the amplitude, but it's always some enhanced behavior. And it's not always related to gauge invariance or things like that. Perhaps even more stranger is that you can use UV constraints to fix CHY integrants. So I'll briefly go over this. Just a very short introduction. CHY amplitudes are given by some integral over integrands that live basically with 1 foot in spacetime and 1 foot on the worldsheet. They're function both of worldsheet variable sigma and momenta or polarization vectors and so on, with some specific expressions given for the sigma model and Yang-Mills in terms of Pfaffians, reduced Pfaffians. So you can ask, well, are there any principles that directly determine these integrands? Of course, there are some ways to get them from ambidextrous strings and so on. But so far, we haven't really known if there's some direct way, some principle that determines the form of these objects. And it turns out that, again, UV scaling can do it for you. And this holds even without assuming any scattering equation. So you never have to worry about solving any scattering equation. You just get the integrands from UV scaling. There's just one minor thing you have to do when you do your usual IJ BCFW shift. You have to shift the corresponding worldsheet variables by Z. And if you do this, you find that all of these relevant integrands for Yang-Mills, sigma model, and even df squared all scale like this. Of course, I'm ignoring some issues if you're doing shifts that involve the reduced particles, but let's not worry about that. So how do you actually do the bootstrap? Well, it's quite simple. There's only one assumption, which is the correct number of space-time dot products and number of sigma ij's. So I start with an ansatz that is totally crazy like this. The denominators have nothing to do with the numerators. Usually these are related, but not in this case. You get a huge ansatz, several hundreds or thousands of terms. You impose UV scaling and permutation invariance, and you find unique results for these theories, sigma model, Yang-Mills, and df squared. And I should say for df squared, there's this tiny bit of extra assumption that I don't allow any dot products between polarization vectors. So that's great. But really, what's great about CHY is that it actually gets us closer to this thing that we're after. So we're after some formalism where we lose maybe locality, maybe unitarity, to gain other properties, make other properties more manifest. And this is the case here. So if we assume something we can call worldsheet locality, that is that any dot product xi or yj only comes in this form with the corresponding worldsheet variables, any term of this form does not scale worse than order z to the -1. Whereas we only need this scaling to get the right answer. So compared to Feynman diagrams, where you might need many orders of magnitude to cancel to get the right scaling, for this worldsheet local objects, it's just 1 power of z that you need to get rid of, and you land on the right answer. So this is for Yang-Mills. If we consider df squared theories or things like this, actually you find that the cycle factors, which have been investigated by these people, actually manifest these right properties. They're permutation invariant and have this right scaling. These are what some of them look like. And of course, this is df squared theory. All of these other cycle factors have E.E products, so they're not the right amplitude. But they seem to be potentially useful building blocks for building things that have the right BCFW scaling. So that's a good thing to look at in the future. So we've added to this list of theories over here CHY. So it looks like UV scaling is winning, at least so far. And here I should say the blue X is because I have to impose that extra condition that I don't get any E.E factors. So this great, this table keeps growing and growing. And of course, the point is not to just fill this table for no better reason, but maybe you never know where this table will crack, and you find the thing that you need to rebuild all of these amplitudes by using other principles. So in the meantime, we can keep classifying and seeing how theories can be fully fixed by fewer and fewer constraints. So now let me turn on to finally discussing color kinematics and how we can use this to expose lower energy strings. So just a short introduction to introduce my coloring notation. I will usually use green for color and red for pure kinematics. And this is the color kinematic duality, which says if you find an amplitude in this form where both C and N satisfy the same algebraic relations, then you win basically two things. First, you win the double copy, so you get to replace a C with an N to get new amplitudes. And second, you win the amplitude relations, which express some relations between different orderings of amplitudes. And you can start using these ideas to bootstrap amplitudes, see how constraining such property is. Just to see some of the simplest examples, because we'll use them a bit later. So the simplest color numerator you can think of at 4 points is just this in terms of structure constants, or you can write it in terms of traces. And this is all you need to build by adjoint theory, right? So you just put in 2 copies of color here, and you select some double ordering that you want, you get this well-known thing. Then the simplest kinematic numerator, which is just linear in Mandelstams, is this. And you might recognize this as the Yang-Mills scalar numerator. So again, you plug it in here, you extract some ordering, you get the Yang-Mills scalar amplitude. Next is the sigma model numerator, which again, you plug in here with your usual color and you get the non-linear sigma model amplitude. So these are some basic building blocks that we'll need in the future. So now we can ask, how can we bootstrap using color kinematics? Well, the first simplest example is the sigma model. And we can sort of ask the question, how many functions, how many solutions do we actually get to the BCJ relations? And with the right assumptions of locality, you actually find that there's a unique solution, which is the nonlinear sigma model amplitude. So by locality here, I mean just quadratic poles, as you expect for the sigma model amplitudes, and of course, right mass dimension and so on. So with the right pole structure and right mass dimension, there's a unique function that satisfies the BCJ relations, and it's the sigma model amplitude. And you can actually prove this by using another soft theorem idea. But okay, now you're done with the sigma model. Recently, we've learned that the sigma model is nothing other than just a linear Z theory. So this gets you thinking, can we do higher derivatives? Can we do the open string, which we know is Z theory combined with super Yang-Mills, or the open bosonic string, or other crazier things like the OP4 sigma model? So it's a natural question. Can we find local building blocks that reach all orders in mass dimension of this form, where both this is in a color dual form? And it turns out that the answer is yes, and just very few building blocks are needed. But your usual building blocks are not good. You have to get some new sort of structures in here. And this is where mixing color with kinematics comes in. So traditionally, the color and the kinematics have been separated. This was always color and this was always kinematics, or some combination of the two. But why not try this following a very simple thing? Just take some numerator like this, which is now a function of both Mandelstam invariants and, say, traces, some random expression like this. And you find that you do find a bunch of new solutions for this type of numerators. And they're actually enough to get you all of Z theory. So you can upgrade your boring old bi-adjoint, which only has 2 colors here. You can replace them with one of these fancy numerators that now has some kinematics in it. You get some expression like this. And now this N carries alpha dependency just because it has some kinematics. You can stick it in there. And this is all you need for Z theory, to all orders in alpha. And the best part is that there is a constructive approach. So you don't just have to worry about getting a large number of solutions and then mixing them in some way. There's a constructive approach to classify all of these solutions. The first step to classify the solutions, and the simplest, is just to dress them with permutation invariants. So at 4 points, there's just 2 permutation invariants, sigma 2 and sigma 3. Any higher mass dimension permutation invariant, you can just decompose into these 2. And then you can use these permutation invariants to address BCJ numerators. And that's because here, if K is a BCJ numerator, then so is this combination, because the sigmas just go along for the ride in the Jacobi relations and anti-symmetry. And similarly, you can do something a bit stranger. You can take a color factor and address it with the same kinematic invariance. And again, this whole combination is now Jacobi satisfying and anti-symmetry satisfying. Next, you can do a color permutation invariant, obviously, where you just sum over permutations of traces, and you can address kinematic numerators with this object. So again, you get some mixed color kinematic object like this. So this was the simplest thing you can do. There's just slightly more complicated thing, which is composing numerators. So it turns out at 4 points, at least, there's a very simple composition rule where you give me 2 BCJ numerators and I give you a third one. So here, if K and J are both BCJ numerators, then so is this combination. And this basically allows you to bootstrap higher and higher on the ladder in mass dimension or in whatever you want. So let's just see how this works with the simplest example. Just start with this, the simplest kinematic numerator, T minus U, for the S channel numerator. Just compose it with itself, and you get precisely the nonlinear sigma model numerator. So it's quite interesting that the sigma model numerator is just a composition of Yang-Mills scalar with itself. Okay, that's great. What happens if you keep going? So let's compose, again, Yang-Mills scalar with nonlinear sigma model. You actually don't get anything new. You just get this thing again multiplied by a permutation invariant. So actually this composition closes quite fast. And that's because in general, any pure kinematic numerator can be decomposed like this in terms of simple scalar, Yang-Mills scalar numerator and the nonlinear sigma numerator. So that's great. But now you can do something really crazy, which is you can compose color with kinematics directly, and you get some expression like this. So here, if C and N are BCJ satisfying numerators, then so is this combination. So we basically have just 3 types of solutions. First is the simplest one, where you just take a color factor and you address it with kinematic permutation invariance. And here I've just added an alpha to match the mass dimension. Next, you have this composition between color factor and BCJ kinematic numerator, again, dressed in the same way. And finally, you have this, where you'd have, again, a kinematic numerator dressed with a permutation invariant color with some dressing. You put all of these together in a big capital C that now has alpha dependence, Mandelstam dependence, C dependence, and D dependence. And this is all you need to build your favorite stringy low energy expansions. So Z theory, you can just get like this. You plug in the C next to a usual color factor, and you can expand an alpha and get all of the terms you want. Then, of course, you can just replace the color as usual with Yang-Mills, and you get the open superstring in this way, which again, here is all the alpha correction in the C's. Next, of course, you want to do the closed superstring. So here, this is the open superstring where your starting point, your C, capital C is given in terms of this. Of course, your instinct is to just replace capital C with another copy of Yang-Mills, but that doesn't get you anywhere. You just get gravity back. The trick is you just have to replace the small c inside of the large C. You just replace this factor with the Yang-Mills. So let's see where you can do that. And the first term in capital C was this. So you just have to replace the CS with the Yang-Mills, which is fine. Then you can try to do this in this type of combination. But if you try to do this, you don't get the gauge invariant solution. So this doesn't get you gravity because it's not gauge invariant. And here, of course, there's no C to replace, so there's nothing you can do. So really, this tells you that all of the higher derivatives to GR come in this form. You just factor out GR, and you can only have these kinematic invariants over here. Next, you can also do the same for the bosonic string. So the bosonic string is again Z theory, which we have in terms of the capital C's. And we just need some new type of numerators for Yang-Mills plus DF squared. And luckily, it's just very few new building blocks that we need. So of course, these things were studied by lots of people over the past few years. And this is all we need. So we just need to add the numerator for F cube interaction, F cube squared plus F4, and so on. Some of these were studied by these people. Again, just dress them with kinematic permutation invariants. You make this big bosonic numerator, and then you stick it in next to your capital C. And this gives you the full expansion for the bosonic string. Of course, it's obvious that you don't get the coefficients you want. This doesn't in any way give you the zeta values. Those you can just match, but the numbers of solution matches, and of course, any term in the bosonic string, for example, is some combination between all of these factors over here. So that was great, but that was just 4 points. You might worry, does this really work in general? And it looks like it does. So this is some upcoming work. We'll hopefully have out soon. The same sort of analysis and the same sort of relationships work in general, it seems. So this was already studied many years ago by Rutger. At 5 points, you have 9 permutation invariant building blocks, which are, you have 8 of them of this form, which is like at 4 points, and you have some extra strange guy like this. Any higher mass dimension permutation invariant can be decomposed in terms of these permutation invariants. And the same is true for the pure kinematic numerators. Above mass dimension 22, any kinematic numerator can be decomposed into lower mass dimension numerators multiplied by these permutation invariant sigmas. There's also a way to compose Jacobi's together. So there's some function capital J, where if you stick in some other numerator, it gives you a higher mass dimension numerator. And this itself closes. So again, you just have a ladder that you can just keep climbing. At some point, this also closes. So you can express any Jacobi in terms of lower point Jacobis and so on. And it turns out that very few solutions are needed to span all of the 5-point Z theory. So that's the whole alpha orders.
Hey, Laurentiu, oh, you're at your summary. Perfect timing.
So just to conclude, it looks like there's many ways to bootstrap many theories. Of course, we know all of these theories are interrelated, but there's a possibility that all of these principles that we thought were different are actually interconnected themselves. It's especially interesting how unitarity in all of those examples just follows from other principles. And it'd be great to know if there's a direct way to see all these connections, especially between the IR and the UV. So it's quite strange that both of these extremes of an amplitude basically contain the same information, right? If each on its own is sufficient to fully constrain an amplitude, they contain the same information. So you might naively think, okay, maybe there's some duality between the IR and the UV. Of course, this is just 3 levels, so it's nothing fancy, but it's still very non-trivial how that might happen, even in terms, how do you get from a BCFW shift to a soft theorem and so on. And what might immediately pop into your mind is conformal invariance. And maybe that plays a role. And of course, this was recently discovered for d-dimensional gravity and was mentioned by Cliff for other amplitudes a few days ago. Another interesting aspect was seeing how CHY integrands follow from UV considerations, and that the cycle factors seem to be special UV objects. So this might be interesting to see if it has any meaning in spacetime. If you take a cycle factor, it has this special UV property. What does that mean for actual amplitudes? Then we saw that there's a few new BCG building blocks that you get by actually mixing color with kinematics. And these are enough to capture the full expansion of the open superstring. And then you need just a few more extra terms to capture the bosonic string. And this in general might point to some interesting structure of how you can just keep composing BCJ enumerators together. This was only discussing the single trace color structure. And of course, this can be extended to double trace and triple trace and so on, which is work in progress. Finally, you can also add in monodromy and other positivity constraints from unitarity. So monodromy also places more constraints on your coefficients and really reduces the number of solutions you get to really pin down, say, Z theory by using just these direct physical principles. And this is also some work in progress. Thank you.
Thank you very much, Laurentiu. That was a nice talk. Yara has a question.
Yes.
Yara, could you go ahead?
Yeah, just for this talk, just question is largely being you get a kind of more insight on the 1/z² behavior in gravity, or
Sorry, can you say again the first part?
You were cutting a little.
Sorry for that. Can you see any kind of more deeper insight for the 1/z² behavior in gravity, or maybe how it can, in this IR-UV relation, how it can be related to soft limits, multi?
No idea. As far as I know, it's still completely magical. The only explanation I have for it is because of permutation invariance. Basically, any permutation invariant theory will have slightly better behavior than you expect. And we sort of expect GR to have at least 1/z, but now because it's permutation invariant, it goes to 1/z². But I don't know, there's probably some better explanation, but I don't know.
Oliver had his hand up. Oliver, would you like to ask your question?
Yes, thank you. I'm not sure whether I got to the exact scope of your claim about how much you can nail out of the disk integrals of the open superstring. Like at 5 points, when you said you get all of Z theory, do you have an all order argument that you get all orders in alpha prime nailed? Or did you just do order by order checks to some very high order?
Yes, just order by order, of course.
Okay.
Yeah, and it's not immediate. So yeah, obviously you don't get any of the coefficients, anything like that, but any sort of term, any solution that shows up in Z theory up to, I forget exactly what order, maybe alpha 6 or something like that.
Okay.
I think which was the highest your great program went, because that's what we used to check. Yeah, so just order by order check.
Well, what's the growth trend as the mass dimension goes on? How does the number of solutions grow that you can generate of your procedure? Does it grow the same way as the amount of zeta values grows, or faster or slower?
You have a few extra more solutions. I can make an exact comparison. Even at 5 points or at 4 points, it grows faster. So there is some redundancy. Well, once you match to Z theory, some of them, well, you don't know, but in principle, some of them could be set to 0. Some of them get in some particular linear combination.
So you mean you do find solutions to color kinematics that are not realized in the open superstring?
I don't know any example, but in principle, it could be true. I don't see any reason why not.
Look at the D to the 8, F to the 5th, zeta 7 of 5-point open superstring. There might be something interesting.
Mm-hmm. Okay, thanks.
Okay, thank you.
So there's a question from James Saint-Germain-Fuller. Could you?
Right, sorry. Yeah, my internet is sort of cutting in and out, but I really like this idea. I think it's wonderful. Maybe this is silly, but if you assume, if you use monotropy as an input, can you fix any of the zeta values
yes,
in Z theory?
Yeah, so that's something we're looking at with Yutin and Jingye and Yihong. If you impose monodromy, then you really cut down on the number of solutions.
But it's not completely fixed.
So the conjecture, I would say right now is that the number of solutions will match the number of odd zeta values. And they
Yeah. You only be able to fix the even ones.
will be related to the other.
Okay, that sounds good. Thanks.
Nima had his hand up earlier. Nima, would you like to ask a question?
My question was just answered.
Ah, okay, great. So I think that takes care of all the questions I see. So I'd like to thank Laurentiu again. And that was a great talk.